Okay, I think we can start. Hi, everyone. Thanks for joining this webinar today, which is the second webinar series between ANIPH project and MAGICBIOMAT. The webinar today will be regarding AI meets biodegradation, digital tools for smarter bio-based materials. Today, we are hosting 3 speakers. Our first speaker will be Dr. Jessica Lalonde from Los Alamos National Laboratory. Jessica received her PhD in mechanical engineering and material science from Duke University in 2024, and she's specialized in predicting biopolymer degradation and properties with data science and also machine learning. And her current research focus on interpreting and also reproducing of biopolymer data handling in ML for applications including material degradation, additive manufacturing, and sustainable aviation fuel biomanufacturing. Thanks, Jessica, for joining us today. If you would like, please share your presentation. You will have 30 minutes as the keynote speaker. And after that, we will have the questions. So for the audience, as you can see the chat box, you can put your questions there for each speaker. And after all the 3 presentations, we will go through the questions and we will answer them. Thank you so much.
Sounds great. Can you hear me okay?
Yes, that's perfect.
Awesome. Thank you so much for the great introduction. Really appreciate the invitation to be here with you all today. I'm very excited to share my research and have a good discussion with you. And I hope that this can open up a conversation for many other topics as well. So I'll go ahead and start sharing my screen.
Thank you.
Can you see my screen okay now?
Yeah, that's perfect.
Awesome. I'm going to go ahead and get started. But please, if you do have any questions, I'll be happy to take them at the end, and looking forward to all the great discussion. So yeah, my name is Jessica Lalonde. I am a postdoctoral fellow at Los Alamos National Laboratory. I started at Los Alamos back in 2019 as a graduate student. And I am now a postdoc, and I have been a postdoc since May of 2024. I'm going to be talking to you today about some of the projects that my research group covers, varying across the polymer life cycle, as well as our special interest in AI and machine learning to accelerate biopolymer design specifically. I have a brief outline here for you to kind of go through some topics of interest. And the 3 questions that my lab is particularly interested in when it comes to AI development for biopolymer materials research are the 3 questions you see there. Particularly, why is it important and why should we consider this technique to be applied to this very, very broad field of material science, as well as what can these techniques tell us that's new? And that experimentally we couldn't learn otherwise. And then finally, what does the existing data look like and how can we harness it to be more capable of developing robust models? I also would like to present to you some case studies, specific examples of how we're applying our data science framework to the polymer science at different areas of the polymer life cycle. And I'd also just like to summarize and discuss with you all. Our research has been going in this area for some time. I think back in 2019, my laboratory invested very heavily in a project involving biopolymer science with a machine learning framework. So we've been doing this for about 7 years now, maybe six and a half. So we are still work in progress and looking forward to learning even more. I can give you a very brief introduction of Los Alamos National Laboratory if you're not already familiar with the institution as a research center. So we're located in the United States. We are in the southwestern corner of the United States. We have a very, very large facility in terms of area as well as in scope. We have a very large research center comprising over 14,000 full-time and technical staff. And the R&D landscape for our material science efforts is pretty vast, with many applications and many fundamental research projects. And if you're not familiar with it, this is kind of one of the examples of the landscape. This is at sunset or right over the Rio Grande River, that winds from Colorado all the way down to New Mexico. And so New Mexico is a beautiful state, and the Research Institute is very diverse and very collaborative. And so it is my pleasure to be able to tell this story to you today based on the excellent research that goes on at this institute. And I'd love to share with you more details about Los Alamos if you're curious, but yeah, I love it. I've lived here since 2019, on and off, and since 2024 full time. It's a beautiful state, and I love the outdoors, and I love the unique landscape. So, very happy to talk more about that if you're curious. And so, one of the first questions that my research lab is investigating is why should we even care about using ML and AI for bio-based materials design? And one of the most interesting parts of our research area is that we can really break it down into three motivations for our research. And the first is in terms of analyzing the complexity of the material science. So, as you know, material science is a very diverse and very intricate field that composes many elements ranging from structure properties all the way to function and performance, all the way through degradation. And so, the relationship of all of the different structural features, all of the different properties, is a very, very time intensive and resource intensive process to be able to make those connections across that full materials life cycle. So, experimentally, sometimes that can take a very long time to examine those relationships experimentally. So, one advantage of using these approaches is to be able to address that level, a next level of materials complexity. It's also about improving the economics of biopolymer design. Many times, commercially, especially for small businesses as well as smaller sectors, these bio-based materials can be prohibitively expensive in terms of scaling up. And part of the reason for that is because bio-based materials come from biology. They don't behave all of the same time every single time. If you put polystyrene into a material, into a water bottle, you know exactly how it's going to behave every single time, and it's going to be the same batch of material every single time. But when it comes to a polymer such as polyhydroxybutyrate or cellulose or starch or lignin or something like this, that's more organically derived, even synthetically, biosynthetically, you're going to have an element of batch variability, and it's going to be more difficult to scale than a conventional material. It's not to say it's impossible, because many people are doing this, and probably many people on this call are doing this, but it can be more challenging and more expensive relative to conventional materials. And the goal is to be able to streamline some of that cost. And kind of along the same lines, we are hoping to be able to use data-rich methods at each stage of this polymer life cycle to be able to reduce that experimental burden, both for researchers as well as manufacturers. So those are some advantages. And so the next question that we are interested in is what can machine learning and artificial intelligence tell us that's new about bio-based materials? And so on the right here, we have a materials tetrahedron, and it's a classical paradigm in material science that's taught to us to be able to relate the different aspect of materials design to be able to fully understand the material. And so when you're trying to understand the structure, the performance of the material, the properties, as well as the processing parameters, these are very, very intricate relationships that often are represented in isolation within different literature examples. But the beauty of AI and ML is that we can leverage that historical and literature data that might otherwise go unused in an experimental design. So you can have decades of access to data rather than just your own personal lab's 5, 10 years worth of research in the background. And another advantage here is that you can use the negative data. We call it negative data in my lab, but it's basically the all of the data that didn't go as planned. It's all the data that kind of failed. It's highly variable. It's highly statistically variable. And while that may be very tricky when determining relationships, it's also very, very good for the model to be able to learn from variability and not get trained on pattern and repetition. Because many times in conventional machine learning materials data sets, you'll have something that's very, very clean, very, very neat. And the beauty of biopolymer data is it's messy and it's noisy in many cases. And that's actually very, very healthy for the model to be able to adapt and be generalizable to many areas of the materials tetrahedron. So the domain expert can build on what we know and then accelerate the scope of their analysis based on applying these very high dimensional feature spaces in each area of the materials tetrahedron. And this is only possible with an advanced data technique. Yeah, this is very difficult to determine these relationships through design, build, test pipelines. But with these kinds of pipelines, you can definitely accelerate those by creating digital twins. You can also determine along your tetrahedron where are your experimental features, such as processing conditions or temperature or different copolymer ratio or additives or blending or even different properties, how each of those features contribute to the model. And we call this sensitivity, feature sensitivity. And you can correlate those features in a way that you can understand why your model is behaving the way it is and how you can improve it with additional data. And this helps you design your experiments in a more efficient way by seeing which experiments you actually need to test. And that's a very, very unique advantage of ML and AI. And so the last thing that I want to talk about in terms of question is what does the existing data look like? So there are large amounts of data, no matter what, across all types of machine learning and AI that are needed to predict, program, and optimize the material life cycle, including biodegradation. But the problem is that many of these data are contained in various data streams and multiple materials profiles. So I will say in general, the literature data and historical data that you can pull from when you're training your models is highly multimodal, high dimensional, and often highly variable, and scattered in many different formats across many different repositories, many different resources, and many different papers. And while that might sound like a disadvantage at first, it takes the community to be able to pool together these resources and have those conversations to see what standards, what normalization practices, and what best practices people can implement to be able to have a unified community and corpus of data. And so part of what I did as a graduate student was I took all of these different multimodal resources and I harmonized them. So for example, spreadsheet or tabular data or visual data like in a scatter plot, or even textual data. So you can use things like natural language processing to do automated extraction. I was primarily focused on manual extraction, which means I went into scatter plots like this and I individually took out each of these pixels as they were represented in a scatter plot and translated them into an Excel spreadsheet. So this way you can take disparate data such as a scatter plot like this or even a tetrahedron plot like this, and then convert it into an Excel spreadsheet. So many different data sources. But the key to all of these practices is to establish a generalizable framework for machine learning and AI. To be able to accelerate that design process. So my lab has broken it up into three components. The first is in preparing your data, and I mentioned that briefly, wherein you may have to do a data collection if you don't already have a pre-prepared data set. And that generally involves going into the literature and manually extracting that data to prepare your data set for a specific application. And the reason why we have to do that is because a lot of times that data is scattered across many different sources. But I believe in the future there will be a widely publicly available library, and there are already many libraries of databases and data sets specific to biopolymers. And you can extract those features to prepare your model. One of the things that I'm working on is codifying the materials data sets to treat biopolymers as materials. I think a lot of times in the literature, biopolymers will be treated as a chemical, and the bio properties will be reported, for example, for starch and silk and, chitin and things like this as examples. And their biodegradation will be reported, perhaps their gas permeability, but their mechanical properties, their thermal properties, they all need to be harmonized and pooled from many different sources. So the next stage of this framework is building a model. So you can train your model with that literature or experimental or simulation data. People also run simulations to collect data, which is very powerful for reaction and kinetic data, particularly with degradation. Then you tune your model and then predict your target property of interest. Your target is your prediction. And then the third stage of this framework is in the deployment and modeling of your monitoring of your model, wherein you can go into that feature sensitivity and see which experimental variables are controlling your model and how you can influence it with experiments. And so I've broken up, in my mind, I've broken up the biopolymer life cycle into 4 major parts. And I want to give you some examples about how I'm applying that framework to each stage. So as I said, design can span many different data streams and profiles, and we can apply that modeling framework to each stage of the life cycle. So as an example, starting with biosynthesis. So my lab primarily focuses on a biomaterial family called polyhydroxyalkanoates, or PHAs. And so PHAs are this family of biopolyesters that are produced by cyanobacteria, by algae, by many different organisms. And there's over 150 unique PHA monomers, which are confirmed so far. And you can derive these both biologically as well as synthetically. And so what my lab does is we take different cyanobacteria, such as Cuprovitus and Escherichia coli, and one way of growing these cyanobacteria to produce PHAs is through a bioreactor. And so this is an example of a bioreactor, and this is an example of some of the features, the little knobs that you can tune over the course of your experiment. And the types of data that you can get out of a bioreactor include a growth curve as well as a polymer production curve. But where does that data come from so you can train a model to improve your bioreactor and thus your yield of PHA? So one of the things that we started with was the literature. And so using manual search, we didn't use an API or anything like that. It involved a postdoc student going through each of these different community resources, database resources, and manually mining that data, which means that I designed a set specific search criteria for each of my studies of interest. And I went through probably about 500 papers individually, and I manually extracted that data, which means that for each plot of growth, as well as production, as well as biomass accumulation and nutrient loss, you can take data from both the text by reading it and manually inputting it into a CSV file, or you can also use a tool called Plot Digitizer, which is a way of taking these little screenshots of your experimental data, uploading it, and then individually digitizing each of these plots. Now, there are tools to be able to automate that process, and I think that there are way more efficient ways of doing this in terms of extracting this type of data. And so one of the things that we as the community, I think we should work towards is that automation process. And one of the papers that I'm working on with one of my students is to be able to quantify what that error rate is in terms of large language model extraction. So using a series of large language models, can we benchmark what that error rate of automated data processing is going to be by looking at both the error rate from the x-axis, the y-axis, as well as featurization of those data points to see if the large language model can correctly classify those data points relative to the manual ground truth benchmark. So the idea is we will be able to get there in terms of automated processing. I just started with manual. So that resource is very labor intensive, but very, very powerful in terms of potential for training. So from that data pool, then you can integrate that framework for machine learning. And so what that ultimately looks like is once you do your feature engineering and remove any missing or outlier, well, we use outliers, but any significantly missing features, you can train your models, you can do a model benchmarking process, and you can look at your sensitivity analysis. Now, in this example, we use sensitivity analysis as a way to design our experiments. And so what we ended up doing was once we trained our model, we broke open the quote unquote black box by looking at how the features are contributing to the model prediction. And from there, if there's a specific feature and you can kind of plot it as a scatter plot of delta values, of model sensitivity values. And what you can do is along that plot of that feature, you can pick out where the model is more or less sensitive. And that's where you can do your experimental prediction to gather that point. And in that way, you can validate your model. And then finally, you can take those experimental points and put it back into your training for an active learning update to improve your quality of your model. And so ultimately, you can get very, very high R squared values and RMSE, nice RMSE values for both examples, such as random forest and gradient boosting, and a variety of other methods. We are applying random forest and gradient boosting to our models primarily because they are so resilient. They can handle very, very noisy data, and you can get high quality results from your model. And so ultimately, what we can do is from your experimental values. So on the y-axis, I'm plotting a fold increase in polyhydroxybutyrate, which is the polymer that we're producing. And for the first 3 experiments, we're interpolating our data. So all of these experiments are testing the phase of growth. So there's a growth phase in which the cells are building up their glycogen reserves, they're building up their energy stores, and then they get into a starvation phase when they actually produce the PHB. But the beauty of testing the growth phase for, day 1, day 7, day 14 is with that we already had all of that data. These are within the scope of our feature. But if you go beyond the scope of your data, and so the longest growth phase I saw someone record in the literature was like 21 days. And so if I pushed the experiment to day 25 of the growth period, that represents an extrapolation of the model. And as you can see, neither random forest nor gradient boosting was able to accurately capture that experimental value, that experimental outcome. But when you have a condition, so now we're switching over to light intensity. So keeping all the light intensity fixed here and now extrapolating beyond the training data range of light intensity. So if, for example, if I am training from 50 to 100 micro Einsteins. I know it's an outdated unit, but going beyond that scope, if you have a lot of data at that upper edge, you can actually generate a strong prediction, even though it's still an extrapolation task. So the takeaway that I wanted to share from this particular stage is that it requires both experimental validation as well as testing what those boundaries of your model are to be able to do an effective extrapolation task. I want to move ahead to manufacturing as an example. So my lab also does 3D printing of polyhydroxyalkanoates. Particularly, we do blends. So the laboratory is very interested in a biopolymer called polylactic acid. It's also a biopolyester. And there are advantageous materials properties that the lab is interested in for prototyping and advanced manufacturing. And these properties tend to include a higher elastic modulus relative and a lower toughness. And so we blend PHB with PLA as a blend to be able to introduce that higher toughness and to be more impact resistant. There's advantages and disadvantages, but to be able to kind of capture the best of both worlds, you want to try and blend things together for an increased toughness. The only problem with this is that PLA and PHB, the performance can be unpredictable. So the properties can be tuned based on the composition, and you want to design a model that can investigate that. And so part of the variability comes from this PHB introducing ductile domains into the blend. And this crystallinity can really impact how energy is absorbed within the blend in these different microdomains. But the problem is as you're adding PHB into your blend, so 15%, 30%, and so on, there may be a blend threshold composition effect when it is no longer advantageous to add PHB. So the question that we were asking was, can machine learning quantify these behaviors? And if so, what is that threshold in terms? We picked toughness, but you could do this for any property, any performance metric. So as many of you are aware, 3D printing is a really challenging thing, particularly with biopolymers. So there are many different things that can go wrong. So in the terms of generating your filament, when you're blending your two biopolymers together, there's a lot of things that can go wrong in the heating and extrusion process for that filament. You can get this kind of weird smoke, you can get thickness deviations, you can get this kind of very rough outcome, and you can also get extrusion inconsistencies when you're actually using that filament, heating it up, and then printing your part. Particularly with PHB, because it is so highly crystalline and it has such a narrow processing window between its melting and glass transition temperatures. There's a lot of issues with nozzle clogging and warping and delamination from the print bed. So a lot of times you'll get this peeling of your print and you won't be able to print the homopolymer PHB. And so that's another reason why we blend. So when we break open our framework for manufacturing, as an example, you can collect that literature data, as we did again, but then we also collected a second data set for in-house experimental data. And when you combine them, then you can benchmark. We benchmarked 6 different models, but these are some examples of the types of models that we ran where you can test and validate your data using different pools of data. And it's often advantageous to do your in-house data as your validation set because it's so customizable. And then you can also break down the process into 3 tasks, which we did for our model. So we weren't just interested in predicting the melting temperature. We weren't just interested in predicting glass transition temperature, because those don't tell you the whole story. Right. So many times people, when they're doing machine learning, they'll focus on one target property, which makes sense because you're trying to optimize for a specific target. But here we were trying to figure out how and why the processing parameters, such as nozzle temperature, bed temperature, and so on, the properties and the composition affect that blend outcome. And so we actually predicted 3 targets in this workflow. We did elastic modulus, we did melting temperature, and we did toughness. And all of that data came from both the literature as well as the in-house experiments that we ran. And so what we were finding is that 3D printing of PHB and PLA blends is highly composition dependent and tunable across the blend space. So as an example, when we're plotting toughness versus Young's modulus, and this represents model simulations, as you increase the PHB fraction, there is in fact a threshold for which the PHB fraction, let's say we're adding 30% PHB. That's actually where we're getting our highest toughness values rather than 50% PHB. So the real variability we're finding is concentrated in this mid-range, not at the extremes. And so from that, we learned that the blend properties are dependent both on the processes as well as the composition. You can't just blend a specific ratio and expect it to turn out the same every single time, because that's not going to happen. But what we did find is that using a SHAP plot, such as this, you can break open your model and do something called an interpretability study. And what that tells you is, as you're specifically predicting a specific target, such as elastic modulus, you can go through each feature in the data set to be able to say, okay, layer height is positively or negatively, in fact, impacting my prediction of that target in a quantifiable way. And that way, you can also relate that to composition. And so I want to move ahead because I'm kind of running out of time here. But so the final point on this particular study is that when you do validation testing of this model, you can actually get a very high validation score based on the mechanical as well as thermal data that you can collect. And the takeaway from that is just that, you know, it's not just the initial blend for the composition. It's not just for the 3D printing blend properties. It's also important to do a validation study of that data to be able to scale. And so for performance, this was some work that we did several years ago, back in 2019, my research group did, wherein you can use machine learning to predict the glass transition temperature of multiple PHA compositions. And this is a more classical machine learning study, more conventional. But what you can do is you can represent your polymer through this simplified molecular line entry system called SMILES. Now, this is a 2D representation of your material. And so what that means is you can translate your individual monomers into a certain number of allowed components. And from those allowed components, you can actually go in and represent it in a SMILES canonical fashion. And once you tell your machine learning model and tell your data set what that representation is, it can then pool from a vast amount of pre-built architectures and pre-built libraries to give you materials property information based on the structure alone. And that's a very, very effective way for designing large-scale models. So in this study, we were doing multitask learning. So we combined a set of PHAs with a set of conventional polymers, and we were able to screen property predictors for a variety of properties to look at candidates for replacing conventional polymers. So you can map each material to a fingerprint and then do that prediction. And so an example of what that looked like is for each conventional material, you can plot it for each different property that we were interested in, all the way from glass transition, all the way down to barrier properties. And then you can do a scale of how you can compare PHAs only to the more conventional material. And so you can do this for a variety of properties. So I want to wrap up really quick. I see the question in the chat and I really want to talk to that person, but I'm gonna finish this really quick. So for biodegradation is my last bucket. And so one of the things that I want to say about this is this has been the topic of my PhD dissertation. And so I have several papers in progress right now with different collaborators on how we can quantify biodegradation and use machine learning to develop profiles for prediction. And so one of the things that our approach looked at was, again, taking the same literature pipeline wherein you start with a repository of data, and you can do that extraction. You can do what we call curve fitting for parameterization. And ultimately what that means is when we're including both PHAs as well as conventional materials like polystyrene, like HDPE, they're going to have vastly different degradation timescales, and they're not going to degrade the same way mechanistically in the different environments. Now, when we're looking at environments like soil, freshwater, and saltwater, one of the things that this approach did was you can generate a curve for each degradation profile. And whether that's mechanical properties or whether that's mass loss, you can determine. But you can calculate a parameter, so like a rate kinetics expression, for example. And you can calculate this parameter of this curve for every single material in your data set. And once you have that curve plotted, we consider that your profile for your material. You can then do a prediction for that parameter and then validate your model, again, through predictions. Now, I want to wrap up because I know this is the end, and I want to talk to people, but I'm happy to go into more detail. So the 3 takeaways that I want to leave you with is, one, in my experience and in my lab's experience, it's important to harmonize as much experimental data with your historical data as possible. There are vast resources of negative data, of structure property data already out there in the literature and in repositories that is just waiting to be accessed, but it needs a lot of manual intervention right now. The second thing I want to leave you with is you can do multi-target modeling to open up new doors for your research across all areas of the life cycle. And you're able to do uncertainty quantification at each stage of that prediction. And it's important to look at multiple targets, not just one in isolation. And the third thing I want to talk about, or just leave you with, is that I think that LCA and TEA analysis in combination with your modeling is very important if you have access to that data, particularly for your material. And I know it's hard with certain materials because maybe the economic data doesn't exist yet for that. But to have a benchmark of where to start, I think will really, really help kind of the future work and the future community. So just I want to say thank you. I know I'm a little over time, but I really appreciate all of your attention and I'm looking forward to talking with you. Thank you very much. And feel free to email me if you want to talk or get in touch.
Thank you so much, Jessica. Your work is really interesting and impressive, specifically the work that you did with extracting data from literature. I have for sure some questions. However, I'm cautious of time. We will move to the next speaker, and after all the presentation, I will come back with more questions. Thank you so much.
Thank you.
So our next speaker will be Margarita Dominic. I know Margarita from MAGICBIOMAT project. She works in DigiTouch. Margarita holds a PhD in computer science from University of Tartu, Estonia, with a focus on an AI that we can explain. In 2026, she received the Young IT Scientist Award from the President of Estonia. Congratulations on that. And at DigiTouch, she contributes to the MAGICBIOMAT project, developing AI models to predict biodegradation, mechanical and thermal properties of materials. You have 10 minutes, and if you like, you can share your presentation, please. Thank you.
Yeah, thank you very much for introduction. I will try to be on time. Okay. Do you see my screen?
Yes, that's perfect.
Yes.
Okay, perfect. All right. Yeah, hello everyone. As Konosh already introduced me, I'm Margarita. I've worked at DigiTouch. I also recently completed my PhD, and in DigiTouch, I'm part of MAGICBIOMAT project, and my goal is to integrate AI models into the project and support the project from technical side. And also the project started quite recently. So currently we are in data collection phase. So a lot of the model results are early because we plan to gather more data and improve these models over time. So this is like a little disclaimer. So this work is part of our package 3, which focuses on AI-powered program biodegradability and circularity. So the main goal is to reduce experimental burden, as was just said in previous talk, and transition to data-driven approach that can predict how materials behave. So we will observe less compositions of plants, and we can interpolate to unseen plants. So at the core, we start from the data. We collect biodegradation curves from partners' experiments, and as well as we are trying to integrate literature data. A lot of points here, like well aligned with the previous speaker. Like in literature, we have a lot of data, historical, and integrating it together with our experimental data is a big challenge, and we are working in this direction. In our project, we have specific polymers of interest, PBAT, PLA, PBS, and TPS. So the idea is that given the composition of these plants, we will build a platform that would be able to predict the biodegradation of any ratio of these plants. And in addition to biodegradation, we also would like to predict mechanical properties such as elastic modulus, strength, and elongation and break. And as well as we would like to predict thermal data, glass transition temperature, melting temperature. So the idea is that we want to find the plant that is stable enough, but also biodegradable. So this interactive platform would give a reasonable overview of how different plants behave, given that a user specifies some ratio. And we incorporate currently 3 environmental conditions for industrial composting, for home composting, and soil. So our modeling approach is based on supervised machine learning. It's data-driven. We compare different models for biodegradation and mechanical properties, modeling and thermal properties. And as input is polymer composition, together with information about environment. So we aim to predict biodegradation and these mechanical and thermal properties. And the key goal is to generalize. So we want to predict the behavior for compositions that we never experimentally tested. Well, to reach this goal, we need to gather thorough data that covers like space of these 4 dimensions, so 3 materials and also TPS. So we started from designing data plan that would cover different ratios between these polymers. So there is a step like 100, 0, 80, 20, etc., etc. And this structured coverage is very important for training the model. And this is collected by our partners. And now to start prototyping the model, to train the model and evaluate it, we need to divide this data set into train and test. So we intentionally remove some of this composition so we can use some part of the data for training and then some part for validation to see how we perform. So this is a usual machine learning pipeline where we observe some data and then we feed some specific AI model for training. So we compare the values during the training with actual target values that were observed by partners. And in this loop, the model is training. And after that, in the second stage, we test the model on these unseen compositions that we left out before. And this is crucial because the information on this unseen composition, like the error that we can calculate between the values that we know versus the values that is predicted by the model, gives us an insight which model behaves better and which composition of model we should pick in order to reach better performance. And on the other side, we can also observe how we perform depending on the region. So this is a different view of these plans, like 0, 20%, 40%, 60. And here we can see that some of the models perform better on one region, while other models on another one. So maybe in the end tool, we would like to use some models for composition of some models for some polymers and another model for another one, depending on how they perform. And this is the same kind of error rates for thermal properties. This biodegradation modeling, the story is a bit more complicated because we want to model the entire biodegradation curve, and therefore we have a lot of points of observations. And one powerful technique is Gaussian processes, because in addition to just giving us a model, it also gives uncertainty estimates of how much we can trust this model prediction. So we compare different models for biodegradation as well. Also, some biodegradation data is coming from the literature. And the idea is that for unseen blend, we can combine models from different curves, and we can use their composition for predicting the blends. So given that we are modeling these three dimensions, I would like to show you how we plan to build our AI-powered tool. So the idea is that the user can select the composition, choose the environment of interest, select the composition of polymer, and on the right side, they would be able to see the mechanical properties prediction. This is already prediction from current model, and then thermal prediction and biodegradation curve. And in addition to that, we also plan to add some literature reference data to see how much we support this prediction. And this is an example of soil environment. Also, the user can select different ratio and see these predictions. And finally, we also collect data with bioadditives and enzymes and compatibilizers. So this is an example of some blends that we have. They were provided by our partners. And of course, with this information, we are like more limited in terms of data. So this is more like for observing this, for this kind of dimensions, we allow to select only small ranges, the ones that we are able to observe. But for polymers, the user can select any ratio from 0 to 100, and then for TPS, it's up to 40%, because after that, there is no point in terms of mechanical and thermal properties. And finally, a very important aspect of these frameworks that we are building, it should be compliant with AI Act, and trustworthy AI is very important part that lies in design of any tool that uses AI in real-world decision-making. And according to European regulations, this ALTAI is assessment list for trustworthy artificial intelligence. It has these 7 dimensions about human agency and oversight, technical robustness and safety that we should keep in mind while designing every tool. So in our case, it means that the models that we are deploying should be transparent for us, so we can, like was also said, look into black box and justify the decisions made by the model. But also another aspect that maybe is important to highlight is that we believe that computational overhead by this tool is minimal compared to the positive contribution to reducing waste, and hoping that this tool will actually reduce this experimental burden, and long-term will produce less waste than additional experimentation. So I know it was probably a little bit rushed, but I was given 10 minutes, so If you have any questions, I will be very happy to answer.
Thank you so much, Margarita. Right on time. That was perfect. And I know your effort and work in MAGICBIOMAT in, let's say, modeling the biodegradation, which is really impressive. And I'm hopeful that the results will help a lot in industry as well. I need to move to the next speaker, and then we'll come back with questions if the time allows. So our last speaker will be Dr. Mariana Kodzabaska from Agricultural University of Athens. Mariana holds a PhD in theoretical chemistry and drug design from the University of Crete and completed postdoc research in machine learning based nanotoxicology at the National University of Athens. She combines expertise in material science, protein biotech, and computational chemistry. Mariana, if you like, you can present your presentation, and you have 10 minutes as well. Thank you.
Thank you very much for the introduction. Good afternoon, everyone. As they introduced me, I'm Mariana Kotsabasaki. I'm a material engineer. I hold a PhD in materials chemistry and design. The last 8 years, I'm a postdoctoral researcher in several universities, such as National Technical University of Athens, where I was involved in artificial intelligence project for materials design and discovery. The last 5 years, I am a senior researcher at the Agricultural University of Athens, and I am also leading the grants writing team, fully specialized in Horizon projects about materials in biomedical applications. Today, I will present you our latest work from the ANIPH project entitled AI-enabled prediction of biodegradability in PHA-based biopolymers. This work sits at the intersection of machine learning, polymer science, and environmental sustainability. Next slide, please. So let me start with the why. Why to predict PHA biodegradation? PHAs are one of the most promising families of bio-based polymers we have today. Unlike conventional plastics, they don't fragment into persistent microplastics. They biodegrade. And that's a critical distinction in a world increasingly burdened by plastic pollution. But here is the challenge. How do we know when and how fast a PHA material will actually biodegrade? The current gold standard involves measuring carbon dioxide evolution or tracking weight or mass load over time. These are valid methods, but they take months and sometimes years to complete. This is where machine learning steps in. Using QSAR models, we can predict biodegradation outcomes from molecular and environmental descriptors in seconds. So our goal was to build a computational framework that automates the entire process, from literature-based data collection all the way to biodegradation prediction in short-chain length PHA biopolymers. Next slide, please. To address this challenge, we developed two complementary machine learning frameworks, each targeting a different measurable endpoint of biodegradation. The first framework predicted mineralization, that is, the percentage of carbon dioxide evolved as a fraction of the theoretical maximum. This tells us how completely a material is being broken down biologically. The second framework predicted weight or mass loss, the physical disintegration of the polymer over time. Both frameworks were trained on curated PHBV datasets assembled following the PRISMA protocol. For mineralization and weight loss, we collected data from more than 30 studies across multiple environments. The model performance, as you can see from the tables, were strong. For mineralization, our random forest algorithm and XGBoost models achieved R-squared values of about 0.95 on the test set, and notably, they generalized well entirely to unseen instances. For weight loss, test R-squared values exceeded 0.93 for both algorithms. Through generalization to unseen data was more variable, something I will turn to shortly. Next slide, please. Both frameworks followed the same rigorous modeling pipeline. We began with the manually rich literature mining. Data was then curated into fair compliant datasets. Pre-processing included factor analysis of mixed data for dimensionality reduction and one-hot encoding for categorical variables. We then trained both random forest and XGBoost models, optimizing hyperparameters through grid search with 5-fold cross-validation. Validation went beyond standard train test splits. We specifically tested generalization on held out previously unseen instances, a stricter test than cross-validation alone. Next slide, please. Now, we organize descriptors into 5 categories. Polymer composition, such as HB and HV molar ratio, additive properties, such as filler plasticizers, etc., environmental conditions, degradation parameters, and biodegradation time in days. The target variable for mineralization model was the biodegradation percentage based on carbon dioxide evolution, and for the weight loss model, we had the weight or mass loss percentage with experimental scale added as an additional feature. Next slide, please. Now, let's look at performance in detail. For mineralization, both models were exceptionally consistent. High R-squared values, more than 0.98. For weight loss, test performance was also very strong, above 0.93 for both models. Next slide, please. Now, one of the most variable aspects of this work was the mechanistic insight we gained from sub-analysis. In the mineralization model, the top predictor was biodegradation time, as of course expected for a kinetic process as it is. Temperature came next, followed by the HV molar ratio, self-erosion, HB molar ratio, and additive concentrations. In the weight loss model, the degradation environment ranked first, which made sense since physical weight loss is strongly driven by hydration and oxygen availability. Time was again highly important, followed by HB ratio, temperature, and additives. Next slide, please. Now, regarding outliers and model reliability, we conducted a systematic analysis of what happened when we excluded outliers. Outliers exclusion decreased model performance across almost all configurations. For applicability domain, we used William plots. Next slide, please. Now, both models are fully deployed and freely available to scientific community. The mineralization tool is accessible at jackpot.org. Users can input HB-HV ratio, additive type and concentration, temperature, time, degradation environment, and degradation mechanism. The output will be the biodegradation percentage over time across all different environments, soil, marine, freshwater, and compost. The weight loss tool is also accessible at the same platform with the same inputs plus experimental scale, outputting mass loss percentage across different environments, real environments, and lab scale studies. All source code is open, fully accessible on GitHub under FSLAO organization, and datasets are archived on Zenodo with a citable DOI. Everything is open access, fully reproducible. Next slide, please. So we presented the first QSAR framework specifically designed to predict both carbon dioxide-based mineralization and weight loss for PHBV biopolymers with different additives and building blocks. Model performance was strong, very high R-squared, above 0.95 for both endpoints. Sub-analysis revealed clear physical insights. Time and temperature dominated mineralization. Degradation environment dominated weight loss. And the HB ratio was a key driver of both endpoints. Outlier exclusion decreased performance. Both models are open access in support of safe and sustainable by design principles under Horizon Europe. Next slide, please. Now, we will see how we can actually use this model in real time. Both models, you can see, are deployed on Jackpot platform. Jackpot is an open access web-based chemoinformatics platform. No installation required, no coding knowledge needed. Getting started, you can sign in using your existing Google or GitHub account, which takes just a few seconds. Alternatively, you can register directly with your academic email address. Once you verify your email, you will have full access to the platform and both predictive models. There is no paywall, no license fee, and no data submission beyond what is needed for the prediction itself. Next slide, please. Now, once you are logged in and have navigated to either model, you will find the interface organized into several tabs. The Features tab gives you a complete overview of all input and output variables, and users can see more details about the independent variables and dependent features, their ranges, units, and types. The Metrics tab on the right lets you examine model performance in detail, and users can examine model performance on the train, test, and validation test. Next slide, please. Now, the core functionality lives in Predict tab. The end users can generate model predictions by either entering a single instance of the input variables, numerical feature as individual values, and categorical features selected from drop-down lists, or by uploading a CSV file using the provided template. Predictions are obtained by pressing the Submit button. Next slide, please. Now, let me show you what the output looks like. Once a prediction is submitted, results are displayed directly in the user interface. For the mineralization model, you will see the predicted biodegradation percentage, that is carbon dioxide evolution, as a fraction of the theoretical maximum for your specified conditions. For the weight loss model, the output is predicted mass loss or weight loss percentage. Results can be exported as a CSV file. This platform flags predictions that fall outside the model's applicability domain. This applicability domain checks is what distinguishes a responsible deployed model from a black box. We want user to trust the tool and to know its boundaries. Next slide, please. Thank you for your attention. You can make your questions.
Thank you so much. It was really impressive. All the presentation today was really interesting, and I think the work that everybody is doing on AI will help us a lot, specifically in industry projects or academia, to move, let's say, to a more sustainable and easier way to generate data, because specifically when we work with industry in our sector, different partners ask us if we can apply AI to reduce the cost and also save the time. So it was really impressive to hear all the work that all of you are doing. we tried to answer the questions in the chat box to save time. Thank you so much from the speakers. I just have one question for Mariana. I think that we didn't answer that in the chat. One of the audience asked that AI is supposed to be based on big data, or they are big C data, and also are these data available when it comes to biodegradable plastic behavior or not? I can mention you can see the.
Yes, where is this
Sure,
comment?
I will
It was me.
reply on that. Yeah.
Hello.
Hello.
Let's see. The question that it says could be for any of the speakers. AI is supposed to based on big data and are big data. This is one. Okay.
Exactly.
Are big data available when it comes to biodegradable plastic behavior? Fonseca, hello. What do you mean if big data are available when it comes to biodegradable plastic behavior? Can you be more specific, please?
Yes, we are like trying to predict the behavior of biodegradable plastics in different ways, biodegradation, mechanical resistance, processability. And you are like getting this data from literature. But my question is really enough data in literature to feed this type of predictive models? Or do we need more research to get a reliable and robust model? That's my question.
Okay, thank you. Actually, there are a lot of data in the literature, especially the last 2 years. We have found a lot of literature-based data, but of course, new experimental data regarding so diverse formulation of PHAs families are always needed. We need for sure new databases from the experimentalists, and after that we could combine all of them, as the other speakers already mentioned, to expand, for example, our data sets that have published in Zenodo specifically, and to discover more about the properties of processability that influencing the biodegradation. We try to find new materials that will be based in big data. You know that polymer informatics is very difficult to have this data because they are not homogeneous. So you need to combine all them together to have better models to predict better all of these functionality and properties that you mentioned. Thank you very much.